Okay, from now on, it is getting recorded.
Okay,
Okay, just okay. Then welcome to Geometry, Arithmetic, and Differential Equation seminar. And today, Ruben from Rennes is going to talk about affine and projective structure and complex manifold. Ruben, go ahead.
Okay, thanks, Christine. Okay, I'm going to start. I'm going to talk about affine and project structure and complex manifold. One is a definition, M is an any dimension complex manifold. Well, two definition, and is affine structure and project structure. And affine structure is an atlas with the transition map is a restriction and affine transformation of CN. Project structure is the transition maps of Atlas is a restriction of an automorphism of PN, projective transformation. This is the definition. So, I'm going to see examples. For example, in general, if N is a quotient who is an open set of Cn, e.g. is a subgroup of automorphism of U without fixed one which adds proper discontinuity on U, if G consists of restriction on affine transformation, then M admit a natural affine structure. Okay? For example, the complex torus admitting an affine structure because it's the quotient Cn between Cn and the lattice. Another example is Hopf manifold. Is the quotient the U is Cn minus 0. J is a linear contraction. It's admit an affine structure. This is an example for affine structures. Examples for projective structure. For example, is for example, the manifold admit an affine structure, then admit a projective structure because the automorphism of the affine transformation, the CA is produced on automorphism of PN. A general example is possible on a quotient. For example, if U is an open set, the PN, J is subgroup the automorphism of the U, the same properties, with the condition is J is only restriction of projective transformation. Then it admits a natural projective structure. For example, PN natural PN is project structure. Another example is the covering by the unique ball. It admits a natural projective structure because of the group of automorphisms of the unique ball is the group special unit of the group the EGLM plus A. Okay, is an example for affine structure and projective structure. The idea in general, right, is the problem is, in general is the classification was complex manifold that admit an affine structure. another example, complex manifold that admit an projective structure some topology property for this type of complex manifold. No? And generally, there exists a restriction of that topology for this structure. So, for example, in the classification, the manifold that admit an affine structure, for example, in the one dimension is easy because M is a compact Riemann surface. The classification is complete. For example, the genus is equal to 0. Then M is a CP1. It admits only natural projective structure. The genus is equal to 1. Is a torus complex. Admit an affine extraction. The set of all the affine structure is isomorphic to C. Okay, if the genus is greater to equal to 2, M is a covering by the unique ball, so it admit one natural projective structure. So it's only three possibilities, no? Only the torus complex admit an affine structure in dimension 1. So the problem is in dimension 2. In dimension 2, the problem is not easy, okay, because it's necessary the new definition.
Okay. Are you sure that in genus at least 2 you have only one projective structure?
Yes, genus, Georgie, genus, what? 2. Yes, yes, only one natural projective structure. Yes, only one. Okay? Other question?
I don't think so.
I don't understand, Georgie.
I don't think so. I think there are several. It can have more than one, no?
Yes. Yes.
What about projective structure on genus 1 case? In genus 1 case.
Genus 1.
Project. Yes.
For example, on the structure de Cn is
Não, Ruben, acho que você não está entendendo. Eu estou falando que em gênero maior ou igual que 2 tem mais de uma estrutura, em alguns casos. Não, e o Rafael está perguntando o que você pode falar sobre as estruturas projetivas em gênero 1. Elas são afins também, automaticamente?
Em gênero 1. Es que no
Sorry to change to Portuguese. It's just to clarify what Rafael asked.
Okay. No, toda estructura afín es proyectiva.
Rafael is asking, what can you say about a projective structure in genus 1?
Se é conhecido ou não, Ruben. Se não for conhecido, tudo bem.
No, o sea, toda estructura proyectiva sobre el torus es afín. Esa era a resposta que queria.
Ah, ok. Isso.
Toda estrutura proyectiva sobre o toro é afim.
Era isso. Obrigado.
Ok. Sorry. Huh? Okay. So in dimension 2, I'm going to the new definition. Okay. The affine connection. An affine connection is an holomorphic connection on the tangent bundle. It's a C-linear morphism. Okay, this is a definition. Satisfy the Leibniz rule. Okay, F is an holomorphic function. Y is a vector field. Two vector. We denote the set this form. Okay, because this is a contraction this vector field. Other equivalencia for affine connection is the same. I prefer this definition because in the case of projective connection, the definition is very similar. Okay, this is the other definition for affine connection. Okay, what is the idea? In the affine connection, you can define two invariants for the connection, the affine connection. Is the torsion and curvature of affine connection. The torsion is defined to us. Okay, is an element in the cohomology. Okay, the connection, the affine connection is called torsion free. The torsion is equal to 0. The curvature tensor of an affine connection is defined to us. Is an element, the cohomology, the set fiber bundle. Okay. If, for example, in dimension 1, set element, como es una two-form, is equal to 0. The same in the curvature. So in the dimension 1, all affine connection, the torsion is 0 and the curvature is 0. Okay? So if I admit an affine structure, then I admit an trivial affine connection. Is defined locally by the zero matrix of one form. The classical theorem say that M admit an torsion-free affine connection with vanishing curvature if only if M admit an affine structure. So there exists a correspondence between the set of affine structure on a manifold, a torsion affine connection with vanishing curvature and the set of a affine structure. In the dimension 1, the set is equal. Okay, this is the classification in dimension 1 because the torsion in the curvature is equal to 0. But in dimension 2, it's not necessary. The classification in dimension 2. The theorem Inoue, Kobayashi, and Oshai in 1918 prove que an complex surface admit an holomorphic affine connection in only if is 4 possibilities: a torus complexum, an hyperelliptic surface, a minimal elliptic surface with the first number bit is good, the PJ is positive, the first class Chern, the square is equal to 0. The minimal surf is not covered by the primary half of the force. In all cases, show that M admit an affine connection in only if M admit an affine structure. This is an equivalent in dimension 2. Okay? The main idea is, first shows that the first class they share, the second class they share is equal to 0. The second idea is using the Genus formula, we can see M is a minimal surface. If M is a minimal surface, there exists a classification of Kodaira for minimal surface. There exist 7 classes. The classification is the main idea for this proof. Okay, this is in dimension 1. But in the proof, it is not clear what is the set of the structures, the affine structure. Kingler, 1998, il show the description of the set of the structure affine. So M is be a compact complex surface after of a finite covering that admit an affine connection. Then, if M is a torus complex, for example, the set of the affine extraction is biolomorphic and analytic variety of the isomorphic class of associated and commutative C-algebra of dimension 2. If M is a primary Kodaira surface, then the set of affine structure is biolomorphic to C. If M is an affine Hopf surface on no surface, then the set of affine structure is a point. If M is an holomorphic principal bundle of elliptic curve over Riemann surface of genus greater to equal to 2 of first Betti number roots, then the set of affine structure is biolomorphic to a complex vector space of dimension 4G minus 3. This is the classification complete and description of the affine structures. Okay. Oh. In the main idea, there exists projective structures. This is, the first definition is a projective connection. So this is the definition. It's very similar for the affine connection, but it is the new terms in the definition, because it's okay. Other equivalence, this equivalence is geometric, because for example, an holomorphic connection on M is given by locally is defined by a torsion affine connection. In the intersection, two connections are project equivalent. They have the same complex geodesic. This is the other equivalent for this definition. This definition is very geometric, because the idea that the projective connection is preserve the complex geodesic. The remark is, if M admit an projective structure, then M admit an trivial projective connection. Okay. Is defined locally by the zero matrix of one form. On this case, is said to be a flat projective connection. Because the classification in dimension 2 is Kobayashi and Oshai in 1918 and 1981 show that the classifications on three possibilities. CP2 is covered by the unique ball in C2 or admit an affine structure. In three possibilities, we conclude that M admit an projective connection is only if M admit a projective structure. The idea is very similar that case on affine connection. The first case is the invariant in the class de share. This is the condition, the class de share. The second Gani shows that M with condition is a minimal surface. It's a minimal first is using the classification of collider for minimal surface. This is the idea, the general idea for the classification. Okay. And there the problem is open in higher dimension. Okay, the problem is very difficult because the problem is in the classification of minimal surface. This is the
Excuse me, Ruben.
So
I have a question. Is this classification works on Keller manifold in
yes,
higher dimensional case?
is very easy the problem for affine connection.
On Keller manifold,
Okay.
this is the same proof. Or am I right or not?
No. For projective connection or affine connection?
Projective connection.
No, it's in projective manifold is there exists the classification in dimension 3 only. In higher dimension there not exist the classification for the projective connection. Okay.
Okay. Thank you.
You're welcome. Well, in higher dimension, for example, for affine connection, for example, M is a compact Keller manifold, for example, Inoue, Kobayashi, Oshai in 1918 proof that M admits affine connection is only if M is covered by a complex Euclidean torus. It's uncovering the torus complex. So, but in general, without condition Keller is not the problem is very hard. That question, interesting question, for example, is if a compact complex manifold M admit an holomorphic affine connection, does it admit a torsion-free holomorphic connection with vanishing curvature? In dimension 1, in dimension 2, M admitting an affine connection if only if M admitted an structure affine is equivalent. But in higher dimension, is false. The answer is not. Sorry, Dumitrescu and Benjamin Mackay in 2009 show that case J is a complex semi-simple Lie algebra that a compact complex parallelizable manifold is the quotient G between G and the lattice does not admit a torsion-free holomorphic affine connection with vanishing curvature. Does not admit an structure affine. Set manifold admit an affine connection always. Okay, entonces this question is not true and general. Another question, for example, is a topology. In dimension 1 is a torus complex. For example, in Keller, admit an affine connection is uncovering a complex or a torus complex torus. So the question is, what can we say about the fundamental group of a manifold that admit a connection affine? For example, in this case, the fundamental group is infinitive. In dimension 2 and dimension 1 is infinitive. So, for example, the theorem Sorin, Dumitrescu, and Benjamin Mackay, 2016, shows that any compact complex manifold with finite fundamental group and algebraic dimension 0 admit no holomorphic affine connection. Entonces, the conjecture is any compact complex manifold of finite fundamental group does not admit an holomorphic affine connection. This is the conjecture.
Ruben, what is algebraic dimension?
Algebraic dimension is the M is a complex manifold.
Transcendence degree over C of the field of meromorphic functions.
Yes.
Okay.
Oh, thank you, Georgie. Thank you. Thank you. Yeah, this is in the case on affine connection. In projective connection, for example, Kobayashi in 1918, M is a compact Keller-Einstein manifold, admit an holomorphic projective connection, then is three possibilities. The first class is positive, M is isomorphic at CPN.
Ruben,
Yes.
that was my question. This Kobayashi theorem.
Okay, what is this question? The answer.
My question is if the manifold was Keller, but it must be Keller-Einstein.
Okay.
In order to generalize the dimension 2 case. Sorry, I forget. I forgot to say the hypothesis Keller-Einstein. Thank you.
Okay. Okay. The first class is equal to 0. Then M is covered by Euclidean torus. If the first class is negative, M is uncovered by the uniform. Okay. The second is the three case is not necessarily Einstein, because remember that Oving and Zhao showed the conjecture, showed that a compact complex manifold with the first class is negative admit an instant Keller metric. No, Zhao also shows that a compact Keller manifold with the first class is equal to 0 admit an instant Keller metric. Okay, it's necessary only for the first class. Okay, this is in general. Another theorem, for example, Yankee and Radov, 2002, shows that M is a projective manifold of dimension n with an holomorphic projective connection. If n is different to CPN, then M is minimal. It's canonical of n is nef. Entonces, in the case of projective, is minimal. Jane and Radov, the classification on dimension 3 for the complex projective manifold admit an holomorphic projective connection. Existing 4 possibilities. CP3, étal quotient was abelian threefolds, étal quotient of a smooth model manifold of false elliptic curves, manifold whose universal cover is the unique ball in CN. In for possibility, is true que admiten an projective connection is only if admiten an structure projective. It's a flat holomorphic projective connection. It's equivalent in the case on projective manifolds. Okay. Oh, c'est fini. Yes. Yes. Bon. Oh, this is.
Ruben, what was false elliptic curve?
Yes. Oh, it's finished. Bon.
It's
Yes.
finished.
Yes. Thank you. Thank you.
Okay. Oh, okay. It's finished, no?
Yes.
Okay. Thank you very much. Ruben. So, what was false elliptic curve?
What questions?
Ruben?
Yes.
Okay. Let's if the other people have questions, then I will. Any question? So maybe I ask, what is false elliptic curve?
I don't remember, huh?
You don't remember, that's why.
Esse termo falso apareceu também na palestra do Javier. Será que é a mesma coisa? Do fake project?
Não conozco um resultado bem recente que eu olhei pouco. Hein?
Tem 18 anos o resultado, Ruben.
Não, que eu olhei o último, não, porque eu estudei mais a teoria do Kobayashi, digamos.
Okay, another question.
So, Ruben, why are you interested in these objects? What is your theorem?
There exists a relation. There exists a correspondence in a complex surface. Okay? There exists a correspondence between the distribution, recap distribution, regular for dimension 1.
Ruben.
Sim.
Olha para a câmera, porque você falando para o lado, o som não está chegando no microfone, a gente não consegue ouvir.
Desculpa. Agora sim. Existe uma relação entre distribuições de Riccati sobre o projetivizado do tangente da surface complexa e as conexões afins. Existe uma
Por que você não explicou isso para a gente? É segredo?
Não, porque isso eu estou escrevendo, como eu estudei muito dessas coisas, então quis falar a teoria geral e coisas que se tem mostrado até agora.
Ok. Obrigado.
Ok.
Eu tenho uma pergunta, Ruben.
Claro.
In English or Portuguese or?
Okay, you can go Portuguese, English.
Or English. Ok, en esas pruebas que aparecía variedade scalar, ¿se usaban a estrutura simplética da variedade ou era somente a estrutura complexa?
No,
En esos resultados de...
Resultados básicamente para usar Keller es que usan la curvatura porque hay una relación entre la curvatura y las clases de Sher. E lo que querem
mas a curvatura depende da forma simplética, não? Da métrica riemanniana que você vai definir aí, ou que vai ser...
Posso fazer um comentário?
Sim.
Posso interromper, por gentileza?
Claro, Maurício.
É porque, como você... Dá licença. É como você tem essa estrutura projetiva, ela induz uma conexão holomorfa. E o fato da conexão ser holomorfa e a variedade ser Keller te dá a restrição nas classes de Chern.
Exatamente.
Claro. Mas se você considera uma variedade Keller que não seja projetiva, por exemplo, aí usa a estrutura simplética.
Os invariantes, basta Keller para você ter condições, não precisa projetiva.
Claro, mas Keller implica uma forma simplética aí.
Normalmente, quando você ouvir falar em uma palestra de geometria complexa, Keller não envolve diretamente a estrutura simplética. Nesse caso, não envolve. Os argumentos estão longe de argumentos métricos, a não ser em teoremas tipo Oban e Al, mas, em geral, é o que estão tentando salientar, é que você tem uma relação entre... Profundamente, vai haver uma relação, mas não... Na maneira que a gente trabalha, você não vê, você não usa a estrutura simplética.
Ok.
Acho que o que é importante aí é que a classe de Atia coincide com a classe de Scherner.
Ok.
E a flatness segue da existência você ter uma classe, né, uma estrutura, uma conexão holomorfa no fibrato tangente. Aí usa que é Keller, nesse caso, eu acho.
Tá bom.
Muito bem. Nenhuma pergunta? Está explicando ainda? Fala, Ruben.
A ideia por trás da classificação de Keller-Einstein é você provar que a curvatura seccional é constante. Essa é a ideia. Aí vem o teorema de geometria riemanniana, se a curvatura seccional é constante, então só tem 3 possibilidades. Essa é a ideia de Kobayashi. Que usa Keller justamente para provar isso, e a invariância que fala Maurício. Você vai ter restrições nas classes de Scherner. Isso te vai produzir restrições. Essa é basicamente a ideia dele. É basicamente isso.
Bom, não tem perguntas. Tá bom, oficialmente encerramos. Mais uma vez, obrigado, Ruben. Próxima vez. Jorge.
Queria fazer uma pergunta sobre superfícies.